To get started, my mic on. Is the battery dead today? You, you can hear me from Zoom? Okay. Can you guys? Okay, cool. I guess it's working. Okay, so to get started, one question I have for you is why is the first hill of a roller coaster the tallest? Why is the first hill of the roller coaster the tallest? And is it possible for the second hill to be taller than the first? Hmm. Why is the first hill of the roller coaster the tallest? Is it possible for the second hill to be taller than the first? Why or why not? Interesting question. Wow, it's because it looks the coolest. Okay, fine, fine, sure, I'll give you that. But why is the first hill of a roller coaster usually the tallest? Is it possible for the second hill to be taller than the first? Graphic organizer if you want to fill it out. You could also just memorize everything. So why is the first hill on the roller coaster the tallest? Is it possible for the second hill to be taller than the first? Why or why not? Hmm. Yes, it's due at the end of the class, but I'm not grading it. So if you don't finish it, that's also fine. If you don't do it, it's also fine. You can take notes by hand if you want. Um, okay, so let's get some answers in the chat here. Why is the first hill of a roller coaster the tallest? And is it possible for the second hill to be taller than the first? Why or why not? Okay. We've got a lot of interesting ideas today. Wow, so many thinkers. Wow. I'm glad to see that some brains are alive. I've always been concerned. You, the TikTok generation. There's a collective. Stop insult. I will. I will insult TikTok all day long. Your brain's turned off. Huh? Is that different? Have I used TikTok? I've seen TikToks, and they're just really dumb. It's not insulting if it's true. Okay, so the first hill is usually the tallest because it gives the most potential energy. The second hill can be the tallest if the roller coaster has a motor. The first hill provides energy proportional to the height, so it should be tall. The second hill could be taller than the first, but then you would not be able to make it over the second hill. The first hill of a roller coaster is the tallest because it gives the car a lot of potential energy, so it can make it over the rest of the hills. It is because where all the energy from the roller coaster comes from is the only hill where you're winched up. Conservation of energy states that energy cannot be created or destroyed. So assuming that there is another winch and gravity exists, no, it is not. Ah, interesting. Okay, so we're gonna continue with today, and we are going to talk about why you are so mad at TikTok because only cool Gen Z kids use it. That's true. I'm very jealous of all you Gen Z kids. Back in the day, what did I use back in the day instead of TikTok? Back in the day, it was Vine. Vine was really hot back in the day. Yeah. What else is really interesting? Back in the day, also back in the day, we had old YouTube. That was back in the day too. We had a lot. There's a lot of nostalgia. Anyways, okay, so roller coasters are powered by gravity. So the thing about roller coasters is that other than the first hill, so on the first hill, your roller coaster is being lifted up by a cable. So that's why you hear the dun 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 as you go up. That's because the cable lift is pulling you up the roller coaster, the hill. After the first hill, though, the cable lift sort of shuts off, and then your roller coaster is at the mercy of gravity. So all of the motion and the loop-de-loops and whatever, they're all essentially being powered by the gravitational potential energy that your roller coaster got from the first hill. So basically, as you go up the first hill, your roller coaster gains a lot of gravitational potential energy that they will use for the rest of the ride. So that's part of the reason why you want your first hill to be really tall, because you want to gain as much gravitational potential energy as you can to use for the rest of the ride. And you're basically relying on that gravitational energy because the rest of the roller coaster, there's nothing else to help you get through it. Oh yeah, but that's also it's. I mean, it definitely adds to the stress factor. But also, I mean, you're also being lifted up by a cable, right? So that's part of it for sure. Okay, so one of the reasons why your second hill cannot be taller than the first is because of something called that you may voice cracking. I don't think anyone notices though. Did you notice? Okay, I voice cracked a little there. Anyways, this isn't middle school. You can't make fun of me for it. So in conservation of energy, so one of the reasons why second hill can't be taller than the first is because something called the conservation of energy. Basically, the idea is you may or may not have heard of this in chem or something. At least I'm pretty sure. I feel like you've heard it in chem before. Heard it in chem. Heard it in chem. Heard it in chem. You didn't take chem yet. Heard it in chem. You didn't take chem yet. Heard it in chem. Yeah. Okay, so the thing is the total amount of energy in the system always has to remain the same. This is what we call the law of conservation of energy. Basically, you can't create or destroy energy. So if we have 100 joules to start off with, that means at every point in the ride, we will always have 100 joules. Not a single bit less, not a single bit more. If we want to change the total amount of energy in the system, we have to do what we call apply work to this. We have to do work to the system. Basically means we have to apply external energy to the system.
I
But
don't
in
like
general,
work.
I'm not in general. What'd you say? What'd you say?
I don't
Oh,
like
someone say
work
something?
though. We don't like work.
We don't like work. But work is so fun. So Can energy be turned into matter? Yes, technically. Can't energy be turned into matter? Technically. But so the thing is, mass is energy. This is wild. This is where we get into like relativity. Mass and energy are technically the same thing. So you can technically turn energy into mass, and you can turn mass into energy. Yeah, yeah. That's it. There's some wild stuff. Um, so yeah, but the thing is, in any isolated system, the energy is always conserved. If you want to change the energy in the system, you have to apply work. But even then, the energy is still conserved. It's just sort of the system sort of gets bigger. You're just, instead of looking at a smaller system, you're now looking at a big system. So in the big system, energy is still conserved, but in the small system, your total energy got changed. The thing is, the law of conservation of energy states that the total energy in the system has to be the same. However, this doesn't mean that the amount of individual energies has to remain constant. So what this means is that you can change energy from one form to another as long as the total energy in the system remains the same. So let's imagine that you have $10. That's a lot of money, $10. That's more than I have in my wallet right now, actually. And so let's imagine you have $10, right? So I can split this between 10 bank accounts. I can split this between 5 bank accounts. I can split this between 2 bank accounts, or I can split this between as many bank accounts as I want, and each one of these bank accounts will have a different amount of money. But the total amount of money I have, $10, will always remain the same. So I can change up how I distribute it any way I want, as long as the total amount of energy, the total amount of money I have is the same. So same idea here, as long as, if I start off with 100 joules of energy, I can put some of it into this kind of energy, I can put some of it into this kind of energy, it doesn't really matter, as long as the total amount of energy is the same. Very, very important. So the total amount of energy has to stay the same, but the ways the energies can be distributed can change / will change all the time. Like the chicken? Yeah, the chicken, it's been there for a while now.
Oh yeah, we talked about this. The chicken should not be raised.
It should. We'll see how long the chicken can last on the board. I haven't found a need to erase it yet. So how do we calculate the total amount of energy in a system? So basically the total energy in the system is basically the sum, sigma, it's the sum of all the individual energies. So I'm going to take my kinetic energy, I'm going to add it to my gravitational potential energy, and then I'm going to add it to any other energies I want to add. These are all going to be included in the total energy I have in a system. So K is kinetic energy, U is gravitational potential energy. Don't ask me why it's U. There's a lot of variables in science, and some of them don't make sense. So in college, I'm pretty sure we use T for kinetic energy, and I think we use V for gravitational potential energy. So there's a lot of like weird variables that you should get used to, that you should just get used to the fact that variable names will change all the time, even between classes. So what I use in this class may not even be the same in another class. So just get used to the fact that these variables will change all the time. But yeah, but the idea is the same. The total amount of energy I have in a system is going to just be the sum of all the individual energies. So this is going to be the K plus the U plus the the thermal energy plus the elastic potential energy plus the chemical potential energy, whatever. Now, usually we will only, not usually, we will pretty much only be calculating the kinetic and gravitational potential energy explicitly. So if you're ever like, how do I calculate the chemical potential energy? The answer is, I don't know. I actually don't know, but you can calculate, a lot of times you can calculate it indirectly. So this is once again relating to the conservation of energy. If you know the total energy in the system always has to remain constant. So basically, if you know how much total energy there should be in the system, and you know how the other energy types are changing, you can sort of deduce how much total energy that particular type of energy should have. So there's a little bit of deduction involved, but that's good. Science is about deduction. Okay, so this is now a quick question for you. What kind of energy would a roller coaster be gaining as it goes downhill? What kind of energy would a roller coaster be losing as it goes downhill? And then vice versa, what kind of energy would a roller coaster be gaining as it goes uphill? And what kind of energy would a roller coaster be losing as it goes uphill? So gaining, losing, downhill, downhill, gaining, losing, uphill, uphill. All right, so in the chat, what are we gaining as we go downhill? What are we losing as we go downhill? What are we gaining as we go uphill? What are we losing as we go uphill? What are we gaining as we go uphill? As we gain downhill, we get faster, right? Usually, I think. So when you get faster as you go downhill, you gain what we call kinetic energy, because kinetic energy relates to the movement of objects. So the faster you go, the more kinetic energy you have. Kinetic energy is, once again, the energy you have from motion. Now, what kind of energy would a roller coaster be losing as it goes downhill? Well, as it goes downhill, that means its elevation is decreasing, which means you are getting closer, lower to the ground. But that means if you're going lower to the ground, you're going to be losing gravitational potential energy, because gravitational potential energy is dependent on how high up you are. The higher up you are, the more potential you have to do stuff. The lower down you are, the more boring it is, and the less potential you have to do stuff. Now, vice versa, if we go uphill, as you go uphill, that means we are going to be getting taller. We're going to be going up. Our elevation is going to increase, which means we are going to gain gravitational potential energy. We basically gain the potential to do fun things. However, what this also means is that we are getting slower as we go uphill. So in general, we're going to be losing kinetic energy as we go uphill as well. So yeah. Yep. So here's another interesting question for you. How would a car braking demonstrate the law of conservation of energy? How would a car braking demonstrate the law of conservation of energy? This is kind of a less intuitive example because it doesn't seem like energy would be conserved, but yet it is. So how would a car braking conserve energy? No, it's braking. Braking. Okay, so let's talk about how brakes work in the first place. So usually when brakes work is you're basically taking your little pads or whatever, and you're basically touching the wheel itself, and you're basically trying to you're basically like sort of like holding onto it, and you're sort of trying to slow it down. And so you're basically, by doing so, you're applying a lot of friction to the wheel itself. And so by doing this, what happens when there's a lot of friction? There's a lot of rubbing. When there's a lot of rubbing, things get warm. When things get warm, that means that there is a lot of heat and there is a lot of thermal energy. So basically by braking, you're trying to convert the kinetic energy into the thermal energy, and the thermal energy, you know, through the calipers and the discs in the car braking system. Yeah, so basically turning kinetic energy into thermal energy. Now, I guess if you have a Prius, you could convert this kinetic energy into electric energy. That's actually how regenerative braking works. isn't, because thermal energy is in general wasted energy. It's just released as heat and it's not really helpful. But if you could convert this kinetic energy into something called, I don't know, into electric energy, for example, that would be really helpful. So that's how regenerative brakes on your car work, is you're basically trying to, instead of converting into thermal energy, you're trying to convert all this kinetic energy into electric energy that you can reuse later. So that's how the brakes on a hybrid or electric car work. Very interesting. Very interesting. Very interesting. Okay, so let's talk about how we calculate kinetic energy.
Very interesting.
So this equation is very important. You will 100% need to know this. For science, for life, you will need to know this. You probably know that you probably might even need to know this for chem, but you definitely will need to know this in the future for sure. So I would just, at this point, I would just suck it up and just memorize it. But I feel like you use it enough where it sort of will become intuitive. It's like you know what F equals. I hope you know what F equals MA. F is equal to MA at this point. Like that should be engraved in your brain. Like you don't even need to memorize it. It's just be engraved in your brain. So this should be the same thing for kinetic energy. You should engrave this in your brain. So the kinetic energy you have is going to equal 1/2 times your mass times your velocity squared. So it's nothing crazy. Nothing crazy. We've seen some crazier equations before. This one, honestly, the kinetic energy is probably one of the most straightforward equations ever. You just have your velocity multiplied by mass. There's no tricks, no coconuts, no butts, no cuts, no butts, no coconuts. No cuts, no butts, no. What's the phrase?
No cuts, no butts, no coconuts.
Yeah. It's like if you're like in elementary school and someone's trying to cut in front of you, you're like, no cuts, no butts, no coconuts.
Or you just sock them in the face.
Never? What do you guys? Okay, this is not a millennial thing. Okay, this is. Have you said it before? Have you heard of that before? Thank you. It's like I'm just like looking at a blank audience here. I really should be looking at Rachel more because Rachel actually understands what I'm trying to. Like that's a very important thing of life. You should know that for sure. You should memorize that for sure. Very important. Yeah. So when someone tries to cut, if a cut tries to cut you, you can just sock him in the face. We don't condone violence here. Yeah, you could just. Yes, I know what socking someone in the face means with a hand. Yes, I know. We don't condone violence here. But yeah, so when someone tries to cut in front of you in Great America, you just tell them no cuts, no butts, no coconuts. Anyways, I don't know how I got up to there, but yeah, basically kinetic energy is 1/2 mv squared. Yeah, know that for sure. Definitely know that. So that's how to calculate kinetic energy. You should also know how to calculate gravitational potential energy. So the variable we will use is U, I think, ish. Sometimes you, honestly, I don't even feel like I have a standard unit for this. Sometimes you'll see, I think you may see this used as a V sometimes. You may also like uppercase V. You also just might see this as being like PE as in potential energy or GPE as being gravitational potential energy. In terms of the variable names, I'm going to be fairly flexible on that. But what matters is that the gravitational potential energy is your mass times gravitational acceleration, which is G, times the height. So M times G times H. M is the mass, G is the gravitational acceleration, which is 9.8 meters per second squared, and then H is the height. So there is also a more general form of gravitational potential energy, and this is one which it's like U is equal to GMM over R squared. So that's like the more correct version of gravity. This is like a simplified case for looking at the Earth. That is more of a general case one for like any object. But when you're looking at objects on Earth, it simplifies into this. So M times G times H. The mass times gravity times height. That is, yeah. So basically, as you can tell here, the more massive the object is, the more gravitational potential energy it has. The higher up it goes, the more gravitational potential energy it has as well. And then G is constant. It's 9.8 meters per second squared. I would say you should probably know this too. Okay, so here's a little note about the gravitational potential energy. We can sort of set any point. So basically, when you're with gravitational potential energy, there's no such thing as having an absolute gravitational potential energy. You instead, the better way of thinking about it is you can define any point as having zero gravitational potential energy. You're basically comparing the gravitational potential of an object to a point that you want to consider. So in terms of what this means is usually we set the ground the ground as being zero. We say that the ground has zero gravitational energy, and we're going to compare the height of every object relative to the ground. And that makes sense most of the time. But let's say I was lifting an object above a table. Well, then it doesn't make a whole lot of sense to compare it to the ground because, well, it's not going to hit the ground. It's going to hit the table. So it actually probably makes more sense to compare the gravitational energy to the table. And so which is we could set the table as having zero gravitational potential energy, and then we're comparing the height of the object relative to the table. So it actually it works both ways. You can always do things relative to the ground, or you could set the table as being zero and then compare the height of the object to the table. It works both ways. The benefit of being able to set various locations as being zero is that you only need to know the height of the object relative to the table itself. You don't need to know how high the table is. So let's say, for example, I wanted to find the gravitational potential energy of the pen that is 5 meters above the table. So if I were comparing it to the ground, I would need to know how high the table is off of the ground, right? So okay, let me draw a little picture here to show you what I mean. Okay, so let's say that we have let's say we have a ball that is, let's say, 1 meter above a table. Okay. So let's say I want to find the gravitational potential energy of this ball. Well, first off, in the ball's reference point, if you think about it, the ball is never going to hit the actual ground here. So it doesn't really make sense to compare the height of the ball to the ground because it's never going to hit it. So it actually makes more sense to compare the ball to the table itself. And so we can set that the table has zero gravitational potential energy, and then the ball is 1 meter above the table. So that actually makes more sense to do so. We could also say that the table is, if we knew that the table is 1 meter above the ground, we could then say that the ball is 2 meters above the ground. But that's just like more work for no reason. So it just makes more sense to be flexible with how we set our zero gravitational potential energy. Usually we will use the ground, but sometimes we can use other surfaces as well to make our life easier. So this is more about being clever and figuring out how to be clever with things. Okay, so so here are some practice problems. So first off, for the first question, if a 1 kilogram mass is being held at 10 meters above a table, how much gravitational potential energy does it have? And how much total energy is present in the system? So let's do this. If you finish 1 early, you can move on to 2 and 3, but we're gonna just do 1 for now. So if a 1 kilogram mass is being held at 10 meters above a table, how much gravitational potential energy does it have? Okay, so I'm going to do the first problem real quick. It should be nothing crazy. So the gravitational potential energy is going to equal U times U is equal to mgh. M is 1, G is 9.8, height is 10. So that means our gravitational potential energy is going to be, what is it, 98.1? What are units? The units are joules. Okay, so that is our gravitational potential energy, nothing crazy. The question is, how much total energy do we have? Well, our total energy is going to equal our kinetic energy plus our gravitational potential energy plus whatever, whatever, whatever. So the thing is, we know what our gravitational potential energy is. This is 98.1. We're not considering any other energies, and we're holding the mass, so it's not going to have any kinetic energy either. So that means our total energy is also just going to equal 98.1. Okay, so now that we know this, let's go to the next question. When the mass hits the table, how much kinetic energy will it have? How fast will it be moving? And how much total energy will we have in the system? So when the mass hits the table, how much kinetic energy will it have? How fast will it be moving? How much total energy is present in the system? So how do we do such a question here? Okay, so I think it probably makes more sense to first do things in a reverse order. So let's first figure out how much total energy is present. So in this case, our total energy energy is always conserved and there's nothing external that's being done. So that means our total energy should still be 98.1. And this total energy is going to equal the sum of our kinetic energy plus our potential energy. Okay, so the first thing we want to do is figure out how much kinetic energy we have. So the easiest way to do this is to take our total energy and look at how much potential energy we will have. So when it hits the table, its elevation is going to be 0, which means that the potential energy will be 0. Which means that our kinetic energy is also going to equal 98.1. So basically, when it hits the table, it has transferred all of its potential energy into kinetic energy. So it's a one-to-one transfer. So now we can use this kinetic energy and we can solve for our velocity. So our kinetic energy is going to equal 1/2 mv squared. So we do the math, we get that our velocity should equal 14 meters per second. Okay, so that's your question 2. Now let's do question 3. When the mass is halfway down, how much gravitational potential energy does it have? And how much kinetic energy does it have? And how much total energy is present in the system? So when the mass is halfway down, how much gravitational potential energy does it have? And how much kinetic energy does it have? And how much total energy is present in the system? Okay, so how do we do this problem? So first off, okay, how much total energy do we have? Once again, the energy is still conserved, so our total energy is going to equal 98, and this is going to equal our kinetic energy plus our potential energy. So I think it probably makes more sense to start with the potential energy. So our mass is halfway down, which means that our height should be 5 meters. So I could do the math. U is equal to m times g times 5. Or I could just realize that, because it's halfway down, that means my gravitational potential energy should just be cut in half. So my U is going to equal 49 joules. This is also, I could also do it mathematically, and this would just be mat 1 times 9.8 times 5. So they would be the same thing. Or I could just, just quickly just realize that the gravitational potential energy should be cut in half. Okay, so how much kinetic energy would I have to have then? Well, the total energy is conserved, so this is 98, and this is going to equal my kinetic energy plus my potential energy. So this means that that 49 plus my kinetic energy should equal my gravitational potential energy, my total energy. So kinetic energy would just be 49. So because the potential energy plus the kinetic energy should equal my total energy, and since I know my gravitational potential energy is 49, this just means that my kinetic energy has to be 49 as well. So that's the general idea. You got to think about what is my total energy going to be, how much kinetic energy and potential energy do I have to have at these various points. The crux is that my total energy has to be conserved, and this is honestly the most important thing that will help you do these kinds of problems. Okay, so next thing we're gonna do is talk about something called. Next thing we're gonna do is do some work. Like fun. Okay. Anyways, so the thing is called work, and then I said we're gonna do some work, so it's like a pun. The jokes are funniest when I explain it.
I get it.
When I explain it. Thank you, I much appreciate it. Yes, the jokes are generally funnier when you have to explain them. Okay, so what is work besides schoolwork? Work is an energy term, and it basically means if we want to change the total energy of the system, we can do work by applying external energy. So we are basically giving the system more energy, and we call that doing work. Now the thing is, work is only done by external energies. If a system is left to just do its thing and be natural and do its thing, there's no work being done. You have to physically add in extra energy to the system to do work. Now in the grand cosmos, energy is still being conserved. So when you apply work to it, you're essentially just transferring energy from somewhere else into the system. So in a bigger system, the energy is still being conserved, but in a smaller system, you got extra energy from work. So if I want to change the total energy of a small system, I can do work to it by applying external energy, and that will change the total energy of the system. So in general, the system will conserve its energy. The total energy will be the same. However, if I apply some external energy to it, if I do some work to it, the total energy will change. The way? Oh my God. Oh my God. Okay, so how do I calculate the amount of work I do? So the amount of work that is done is just basically going to equal the amount of the change in the total energy of the system. So if the total energy of the system is not changing, there is no work being done. If the total energy of the system is changing, then there is work going to be done. You can also calculate the amount of work being done as equal to the force times the distance. The force you apply times the distance you apply. I don't know how much we'll use this second equation, this year. I don't know how much we will use it, but if you do take APC, I'm sure you will use it there. This would actually equal the integral of F times ds. But I don't know how much we would use this in this. We'll see. I don't know how much we will. But you'll definitely need to know that the work is going to equal the change in the total energy of the system. So you can actually think of it, this is actually the definition of work, but just more in a more equation sense, if you like equations more. If you're one of those people. I like equations. Equations are cool. Okay, so that is how you basically calculate work. You can just calculate work by the change in the total energy, or I can figure out my work as equal to my force, the force I apply over the times the distance I apply the force over. So if let's say if I'm like pushing a car or something with a certain amount of force over a certain amount of distance, the total amount of work I do is going to equal that. Okay, so that is how you calculate work. Let's do a couple of work practice problems. So back to a roller coaster once again. If a 1,000-kilogram roller coaster is going down from a 100-meter tall hill, how much work is being done in the system? Then in the vice versa, if it's going uphill, how much work do you have to do to bring a 1,000-kilogram roller coaster to the top of a 100-meter tall hill? You can assume that in the second question that it's initially stationary. And same with the first one. So how much work is being done when a 1,000-kilogram roller coaster is going down from a 100-meter tall hill? How much work do you have to do to bring a 1,000-kilogram roller coaster to the top of a 100-meter tall hill? Okay, I'm going to answer these questions and then I will continue. So first off, I have the 1,000 kilogram roller coaster is going down from a 100-meter tall hill. How much work is being done in the system? So the first question I have for you is anything externally being done in the first scenario? Is there anything externally being done when it's falling down? Am I doing anything? So if there's nothing being done, is there work being done? So for the first question, there is actually zero work being done. Exactly. There's actually zero work being done. Wow, that's mind-blowing, huh? So, and that's because if we actually do the math, all of this gravitational potential energy will get converted to kinetic energy. But yeah, no work is being done in the first one because nothing externally was being done. Now, for the second question, though, will a roller coaster want to go up the top of the hill by itself? Do we have to do anything to push it to the top of the hill? Do we have to do anything to push it to the top of the hill? Okay, so yes, I agree. We do have to do something to push it to the top of the hill. So do we have to do work to do that? Yes. Okay. So for the second question, we do have to do work this time because it won't want to go up to the top of the hill by itself. So the amount of work we have to do is going to be equal to the amount of the change in the energy of the roller coaster. Initially, the roller coaster is not moving and it has no elevation. So it has zero total energy initially. I guess you can call it as the energy, I guess let's call it energy initial and EI. The initial energy it has is zero, is nada, because it is not moving and it is on the ground. So when I push it to the top of the hill, at the top of the hill, let's call this, I guess, E top, the amount of potential energy I'm going to, it's I guess we're going to assume that when it's at the top, it's also not moving, just to make our life easier. But when it's at the top, it's going to have potential energy, and that's going to equal m times g times h. And this is going to equal 1,000 times 99.8 times 100. And this is what, 980,000, right? Okay, so this is how much gravitational potential energy it will have when it's at the top of the hill. And initially, I had zero total energy. This is how much total energy I have at the top. So the amount of work I have to do is going to equal the difference between these two energies, which means the work I have to do is going to equal 980,000. And that's partially because I have to do work to lift it to the top. In the first question, I do not have to do work to make it want to fall. It's going to want to fall on its own. However, to make it go up the top of the hill, I will have to do work. Okay, so there's a little bit of an interesting thing with the second one. So you could potentially, so if the roller coaster was already moving at a very high speed, then it could be possible for it to go to the top of the hill without you having to do work, right? So like if I was moving really fast and I just let it go to the hill naturally, it will make it to the top without any work being done, right? Because it's like if it's moving very fast and I just like let it slide up to the top, that's how like an actual roller coaster works. It's going very fast and then it sort of slows down as it gets up. Then it's possible for it to go up to the top of the hill with no work. But in this case, initially was not moving, so I would have to push it to the top. Okay, so that is pretty much, I think, it for today in terms of the content. Do I have anything else? Oh, last question. Just want you to answer this real quick. Would it be possible for a roller coaster to go up a second hill taller than the first? I know we answered for the warm-up. Try to re-answer it with your knowledge that you obtained from today. And then after that, we should be pretty much good to go. And then you can do whatever you want to do.
We can do whatever we want to.
So we have 1 minute left. So we're going to continue our energy stuff on Friday. But other than that, I'll see you guys on Friday.
Thank you.
Thank you.